We've spent the past couple of lessons looking at how electrons can either absorb or emit energy. In this lesson, we'll be looking at how electrons arrange themselves around the nucleus in the quantum mechanical model. By the end of this lesson, you should be able to extract information about electron arrangements directly by the location of the element on the periodic table. So here's Bohr's model. Remember we said that Bohr's model kind of broke down after a little while and really only worked for hydrogen atoms or hydrogen-like atoms. And it's not that Bohr's model was exactly wrong, it was just missing some of the finer details. So for example, in that first energy level, there is just a single energy level. In the second, there's actually two sublevels to that energy level. In the third, there are three, and in the fourth, there are four, and so on. Now, I kept mentioning that notice how close together those energy levels in the Bohr model, how close they were getting together. And that's because when you start talking about the sublevels, you can see that they start crisscrossing in a sense. And so these first two sublevels for the third energy level are at a slightly lower energy level than the first one for the fourth energy level, and then we go back to the third, and so on. So in development of the quantum mechanical model, they were using evidence that some spectroscopists had come up with. And so this next bit is kind of a mixture of quantum mechanics, a little bit of the older spectroscopy terms. So in the first energy level, n is equal to the energy level. It's the principal quantum number. There is one s orbital. Now the s comes from spectroscopy. They noticed that if s orbitals were involved, you had very sharp lines, very well-defined lines. In the second energy level, we have an s orbital, which is this inner line, and then we have three p orbitals, all at exactly the same energy level. So this second ring in the second energy level is three separate sublevels sitting on top of each other because they're all at exactly the same energy. In the third energy level, we have an s, the three p's, and then five d's. So here's our s, there's our p, and then the five d's are out here in between that's where they start crossing around. And then for the fourth energy level, we have an S, 3 P's, 5 D's, 7 F's. Oh, I forgot to say, P is for principal. It was a very prominent line. And D is for a very diffuse line, is what the spectroscopist noticed. And then F orbitals were for a fundamental line. And these were very high energy type lines that were generated in the spectra that they were looking at. After that, the spectroscopists weren't able to make any more contributions because they didn't see any more lines. So quantum mechanics says, well, any additional orbitals after this are going to follow the same pattern, but the names are just going to be alphabetical. So the next one in the fifth energy level would be an S, the 3 P's, 5 D's, 7 F's, and then 9 G's. So let's get rid of the diagram. And we're going to look at kind of a comparison between Bohr's model and the quantum mechanical model. So each orbital, just a side note, this will help explain some of the stuff later on. Each orbital can hold a maximum of 2 electrons. So in that first s orbital, we put our 2 electrons. And notice this is the same as what Bohr said that we had in that first energy level. And then for the second energy level, we have 2 electrons in the s orbital, and then we have a total of 6 electrons distributed amongst the 3 p orbitals. Add those together, and we get a total of 8 in the second energy level, which is in agreement with Bohr's model. So then we go on, so we have 2 in the s, total of 6 in the p's, total of 10 in the 5d orbitals, 2 electrons per. Add them up, and there's that 18 that we had from the Bohr model. And then the next one, remember Bohr said 32, is the next maximum number that are allowed in the fourth energy level. So we got 2 in the S, total of 6 in the P's, total of 10 in the D's, total of 14 in the F's. Add them all up, and there's that 32. So Bohr wasn't wrong, he was just missing some of the finer details. He didn't know about those sublevels. So here's our lithium atom using the quantum mechanical model. As I said in the previous unit, it is not feasible to start trying to draw all the speckles for likely locations for an electron. So instead, we're going to define a three-dimensional region in space within which there is a 90% chance of finding the electron. So it wasn't just random that I picked this particular shape. It turns out that s orbitals are shaped like a sphere. Now you have to remember, these things don't actually exist in reality. It's all math, it's probability. So s orbitals are radially symmetric around the origin of the xyz coordinate axes. But it's much easier just to think s orbitals are shaped like spheres. And then we have the 3p orbitals. We've actually seen this diagram before. In books and other official documents, they will say dumbbells like a hand weight. But my students, probably because I've been using this picture for years, they say, no, they look like peanuts. And because peanut starts with P, it makes it easy to remember that p orbitals are shaped like peanuts. They are different. They look like they're all the same thing. They have the same, put it in air quotes, shape. So we have one that's lined up along the x-axis, another one that's lined up on the y-axis, and then the last one is lined up on the z-axis. So they have their own space. And another thing to remember is that even though it looks like we now have twice as much area to put electrons, you can put more than 2, it's still 90% chance of finding a maximum of 2 electrons somewhere inside this shape. So sometimes both electrons are in one lobe, sometimes they're split evenly, sometimes they're in the other lobe, and then 10% of the time they can be someplace else altogether. All right, so the next set of orbitals, we have the 5d orbitals. And the way I tell my students to remember the shapes is that they are double dumbbells. Now again, this is all math, and so these guys, their shape is a little bit different than this one, even though they're all still d orbitals. For anything that's lined up on the z-axis, the requirement for various reasons is that they have to be symmetric, radially symmetric around the z-axis. So the only shape that gets that is a dumbbell with a donut. The other ones are allowed to have different variations. They don't have to have that symmetry. All right, so here we have the f orbitals, all 7 of them. They have the same issue. Here's the one that's lined up on the z-axis. So symmetry demands that it be completely symmetric on the z-axis, which means we have a dumbbell with 2 donuts. The other ones, the only thing I've been able to come up with to remember their shape is that they look kind of like freaky flowers. Got petals all over the place. I've never been able to keep track of whether it's one that's got 2, 4, 6, or if it has 8. So yeah, freaky flowers. And then I actually did spend years trying to find an image of the g orbitals. So I was really happy when I finally did find one. Now, if you go out and you look on the web, they pop up all over the place. I guess it was just a case of they didn't really have the computing power to calculate what they look like. And I recognize these patterns in the coloring as very much a mathematical program that they had to use to calculate them. And notice we got the one that's vertical, which means it's oriented on the z-axis. and it's a dumbbell with 3 donuts. Math likes patterns. All right, so the next part, we're going to go over orbital diagrams, which shows how the electrons will arrange themselves into the different orbitals. So we have the orbitals labeled, it's like this bottom box represents a 1s orbital. And then the next energy level that we have is a 2s orbital. And then the next one up, we have the 2p orbitals. Remember, they're all at the same energy level. So that means that all 3 of the orbital boxes are going to be in the same horizontal line. We're also going to be looking at electron configurations. Electron configurations are just a shorthand notation for the information that is provided in the orbital diagrams. All right, so we're just going to start with hydrogen. Start with the simplest and work our way up. So hydrogen has 1 electron. The lower energy everything is, the more stable it is. So that means the most stable arrangement would be for hydrogen's electron to be in the 1s orbital. Now, this drawing I have here is not a 1, it is a half arrow. So electrons behave as though they are spinning on their axes. If they are spinning clockwise, they're spin up, and if they are spinning counterclockwise, they are a spin down. And their magnetic spin value is 1/2. So this is why I used a half arrow. Also, half arrows are a lot easier to draw when you're doing a whole bunch. The only requirement when you're doing these is that you have some kind of point on the arrow so that whoever's looking at it can tell that you know that there's a difference between spin up and spin down. And then by convention, we always put the spin up arrow in first. So that is the orbital filling diagram, a 1s box with a half of an arrow in it. The electron configuration would be 1s1. So what this tells us is that we have a 1s orbital with 1 electron in it. So let's go on to the next one, which is helium. So we have 2 electrons. So we say, all right, well, I can get a maximum of 2 electrons in each one. The Pauli Exclusion Principle says that the only way you can get 2 electrons in the same orbital is if one is a spin up and one is a spin down. There's a couple of reasons why, but probably the easiest one to kind of think about is that those electrons have spin values. They're charges that are moving or spinning. It gives them magnetic fields. And so one has the North Pole up and the other one has a North Pole down. And so even though the electrons are repelling each other in that orbital, those magnetic fields are helping stabilize them a little bit. So Pauli Exclusion Principle, 2 per, provided one's an up, one's a down. And then the electron configuration would be 1s2. We have a 1s orbital with 2 electrons in it. So we're going to go to lithium. So we go 1, 2, there's our 3rd electron. So the idea that we're going to start from the very bottom and work our way up to the higher energy levels is called the Aufbau Principle. It just says that you start from the lowest level and you work your way up, making sure that you fill the lower energy levels up before you can move to a higher energy level. So kind of ask yourself, what is the electron configuration? And I'll click it in just a second. So we have an electron configuration of 1s2, 2s1. Now there is a tendency, because of experience with math, that to leave that 1 off because mathematically it doesn't do anything. But this is not math. That's also why it's not 1s squared. This is a notation. So it says 1s orbital, 2 electrons. 2s orbital, 1 electron. So make sure you always include your numbers. All right, so the next one, we're going to do carbon. I'm going to skip over a couple because they don't really provide any additional information. So carbon has 6 electrons. So we start from the bottom. 1, 2, 3, 4, 5. And this is usually where I stop the lecture and I say, okay, so where is that next electron going to go? And just because we have this pattern of filling up the boxes before going on to the next one, a lot of my students will say it will go into the same box. Now you have to think about the fact that electrons repel each other. So if there is an empty orbital available at the same energy level, it would much rather go into its own orbital. So the orbital filling diagram for carbon actually looks like that. So this idea that we are going to fill up energetically degenerate orbitals, so orbitals that are at the same energy level, with singles before we start making pairs is called Hund's rule. And I found out that there was indeed a Dr. Hund, his German name. His name was Friedrich Hund, and he was a German physicist. An additional part to Hund's rule is that the electrons, when you're filling them up with singles, all have to be in the same orientation. And since we're starting with, by convention, with the up arrows, you're going to fill these boxes up with 3 up arrows before you start adding the down arrows. So electron configuration would be 1s2, 2s2, 2p2. Now this is where you lose a little bit of the information from the orbital filling diagram by going to the electron configurations, because unless you know that we have 3p orbitals and they're all at the same energy level and that they're going to, Hund's rule says they're going to be unpaired, you're going to just think that maybe that's a pair. Another reason why knowing whether you have paired or unpaired electrons is that when we start talking about bonding, wherever you have unpaired electrons, they're going to form bonds, because unpaired electrons are unstable when you start talking about bonding. That's why they form bonds, because they can get more stability. So we go on. So now we have scandium. And so I'm just going to kind of go along, and I'm going to keep track of the total electrons so I don't lose track. We're going to start from the bottom, Aufbau Principle, and work our way up through the energy ladder. So there's 1, 2. Next level up is 2s, so 3, 4. Then we do 2p's, and we're going to fill them all up with singles first. 5, 6, 7, 8, 9, 10. And then we go up to 3s, 11, 12. Next energy level is 3p. So 13, 14, 15, 16, 17, 18. And then you say, all right, next one up is 4s. So 19, 20. And then that last electron, we look at the y-axis to make sure we don't get confused by this diagram. So the next energy level, sublevel, is 3d. So our electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Now this is called a complete electron configuration. It's also done in the filling order. If you go and you look it up on the web, and there's a lot of periodic tables that do it this way, if they list electron configurations, they will list them all by energy level. And so they're going to put the 3D down here with the 3P. I don't care for that. It's also a really good way to check students that aren't figuring this out on their own. They are just Googling stuff. I like to have it in the filling order because that makes more sense to me. Now, scandium is only element number 21. We have 118 elements at the present, and that would be a really long electron configuration to try to write out. So there is a shortcut, and I'm going to show you how to use the periodic table to get the shortcut. But for right now, we're going to say, well, these first 18 electrons, they correspond to argon. And so argon is element number 18. So scandium is a lot like argon, but it's got 3 extra electrons. So the way we say it's like argon, or it has an argon core, is we put it in square brackets. So that way we're telling whoever's looking at it that it's not argon, it's an argon core. And then we add the rest of it on there, and we say, okay, well, it's got the argon core, and then the extra electrons are 4s2, 3d1. And this is called the noble gas electron configuration. It's a shorthand for the shorthand. All right, so electron dot structures. We did a little bit of this when we were talking about the Bohr model to begin with back in the first unit. And the reason why electron dot structures are important is because they show the electrons that are available to chemically react, to participate in forming bonds and reactions. So those electrons in the highest energy level are the ones that do that. They're called the valence electrons. There are two rules for this. Electrons 1 through 4 are added singly. And then once you have the 4 singles and you want to add them like sides of a box, don't make circles. The electrons 5 through 8 start being forming pairs. And I have some examples so you can see what I mean by this. So the first example, what is the electron configuration of strontium? So we go and we get our orbital filling diagram out and we figure it out. So the valence electrons are in the highest energy level. The highest energy level, the big number, is 5, and there are 2 electrons total in it. So therefore, strontium has 2 valence electrons, and it will have 2 dots. So sides of a box. It doesn't matter where you put them, as long as you don't make a pair. So I put one on top and one to the side. You could do one on top, one on the bottom, or you could do one on the side, one on the other side. It doesn't matter. Next example, what is the electron configuration of nitrogen? So we do the same thing, and we see that we have our highest energy level is 2, but it's split between the 2s and the 2p. So that means our valence electrons have to be added together because we have a total of 5 valence electrons. So our electron dot structure is going to have 5 dots. So we put the symbol in the middle and add the 5 dots, and we're going to end up with 3 singles and 1 pair. It doesn't matter where the pair ends up. It just matters that you have 1 pair and 3 singles. I like putting them on top because they look like a little hat to me. And again, the important part is knowing how many unpaired electrons. So looking at this electron dot diagram of nitrogen, you can see that nitrogen is highly likely to form 3 bonds. So electron configuration of xenon, that's a really big one. So again, we have a total of 8 electrons shared between the 5s and the 5p. So we have 8 dots. So we end up with an electron dot structure that looks like that. When you are drawing electron dot structures, you will never have more than 8 dots. So if you end up with more than that, you need to go back and check yourself. Also notice, and I've noticed this when students start doing these ones that are getting a lot of dots, it is not a circle. It is sides of a box, because we have to be able to see which ones are singles and which ones are pairs. All right, so this next part, it is inconvenient to try to use those orbital filling diagrams all the time to figure these out. So I'm going to show you a technique that takes advantage of the structure of the periodic table in order to read those electron configurations directly off of the periodic table. So to your periodic table, this is a different one, sorry. One of the other things that we can extract from this is the valence electrons. So we don't even have to write electron configurations in order to figure out what the valence electrons are. And it's the tall columns. So everything in group 1 has 1 valence electron. All the elements in group 2 have 2 valence electrons. And we will see shortly that all of the elements in the transition metals and in the inner transition metals also have 2 valence electrons. There are some exceptions, but we're not going to worry about those. And then group 13, they have 3, 14 is 4, 5, 6, 7, and 8 for neon through radium. Helium only has 2 electrons, so that means it can only have 2 valence electrons. It can't have 8 just because it's in that column. All right, so here's where we want to have a periodic table out. We're going to add some information to it. First thing you want to do is you want to number the rows. Each one of the row numbers corresponds to an energy level. The first two groups and helium correspond to s block elements. Groups 13 through 18 correspond to p block elements. The transition metals are d block elements. Notice that it says n-1. This means that the energy level has dropped by 1, and that's because those sublevels are crisscrossing at this point. So you can either remember it, or something I found is a lot more helpful is you just write it down on the periodic table. So this first row all the way across, they're all going to be 3Ds. And then we have 4D all the way across, 5D, 6D. All right, so notice that there's a jump in the numbers as you go between lanthanum and hafnium and actinium and rutherfordium. And that's because the F block actually sits in there as far as how they work. Unfortunately, the F block has a lot of exceptions to it. So we're going to adopt a strategy that is how I learned it. I don't know if it's good, bad, or indifferent. But you go across, and we're going to connect the upper corner of barium to the upper corner of cerium, and the bottom corner of radium to the bottom corner of thorium. So the intertransition metals are the F block. They drop by n-2, and I cannot ever remember to do the n-2 part, the energy level. So I just write 4F and 5F next to the lanthanides and the actinides. I think that's all of the information. So let's go and take a walk down periodic lane. All right, so I realized when I first started teaching this that I always told students to imagine they were kind of walking across the periodic table. And so that's the analogy I'm going to use for this. So I've got a little guy who's going to walk across the periodic table. Every time he steps into a box, he is adding an electron to an orbital that corresponds to the type of box he steps into. And so for the first box, the first thing he's going to step into is an S box in the first row. So he goes. So we have 1s1 for hydrogen. Goes across to helium, steps into a second S box in the first row. So the electron configuration is 1s2. Then we keep going. Remember the Aufbau Principle, we always have to start at the beginning. So we have the first row is going to be 1s2. He goes off the periodic table, continues on with the second row. So lithium would be 1s2, 2s1. Beryllium is 1s2, 2s2. As soon as he steps over here onto boron, he is now in the P block, which is why boron is 1s2, 2s2, still in the second row, 2p first box, so 2p1. Now the animation was getting too difficult, so he's just going to kind of fade in and out at this point. So we have, keep clicking, carbon would be 1s2, 2s2, 2p2. Nitrogen would be 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. We're just stepping over into the next box each time. So we're adding one electron to whatever box we're stepping into. So now we have fluorine, which would be its next box over. So 1s2, 2s2, 2p5. And then neon, 1s2, 2s2, 2p6. So we're just counting boxes and keeping track of which block we stepped into. All right, so we have chlorine. So chlorine's over here. Now there's two different ways we could do it. We could do 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5. Or we could also say, well, let's try to get a handle on this noble gas core, because I have the feeling that you're going to be looking at some really heavy-duty ones. So the way you figure out what core you have, you go up one row all the way to the end. So this is the same as neon with some extra electrons on it. So neon is element number 10. So these first four would be the neon part. So it's going to be neon 3s2 3p5. The other way you can do it is you say, all right, well, I finished off the second row. So I'm going to start over here. We have 3s2 3p5. Next example would be nickel. So let's do the core first. So up one all the way to the end. So it's argon, and then it's 4s2. Remember, we stepped down by 1, so 3d, and then we count the boxes over, 3d8. So there's the complete electron configuration, and there's the noble gas core. Like I said, a lot easier to write. And then rubidium. My students really like the core when I start doing this. So here we are. We know it's going to end in 5s1. So all we have to do is find our core. So it's a krypton core, 5s1. All right, so I have some more examples. We have yttrium, and I just put the atomic number on there to make it a little bit easier to find. So we find our core. It's a krypton core. I need to select the pen. Yeah. So we have, get my pen down here. So square brackets, krypton core. Finish the square bracket. And we come back, it's going to be 5s2. And then we want yttrium, which is the first one, 41. Now we got bromine is the next one. Bromine's over here. It's number 35. So we have an argon core. So we have finished off the third row. So we have 4s2. You have to go all the way through the 3D row. There's 10 boxes. So 3d10. And then 4p, 1, 2, 3, 4, 5. Then we got calcium. So calcium's core is argon again. We have, and then it's just 4s2 for calcium. And then we have tungsten, which is right there. So we go up one all the way to the end. So it has a xenon core. And then 6s2, so we're right to there. Now remember, we got these little dashed lines to remind us to go down through the 4f. We're going to go all the way across. You might want to write on your table that there's 14 boxes, just so you don't have to keep counting. So we have 4f, 14. Then we go back up to here, and we say, all right, we're back in the 5D. So 5D, 1, 2, 3, 4. All right, so that's an example of how to do that. All right, so wrap up. Electron configurations describe where electrons are most likely to be. It is not like the Bohr model where we have those fixed paths. The periodic table is organized by electron energy. It's also organized into blocks, which allows us to directly read the electron configurations off of it. So remember, we have groups 1 and 2 in helium are S. Groups 13 through 18 are P. And then groups 3 through 12, I'm trying to do this in my head, are the transition metals are going to be the D block, and then the intertransition metals are the F block. The row number it corresponds to the highest energy level that is occupied. We actually saw that with the Bohr model in Unit 1. And then once you get a handle on the patterns, and that's part of what we're trying to do this unit, you can read electron configurations directly off of the periodic table. You can get the valence electrons, all kinds of information off of the periodic table. So that's it for this lesson. And next time we'll be looking at a little bit more at some more information that you can extract from the periodic table. Thanks for listening.